All right, recording is rolling. Welcome to Tuesday, November 30th. The midterm schedule was just released yesterday. Well, here's the quick rundown on this. Uh, these are the last few days that we're going to meet in December. If you want to see the full breakdown, then I posted this file to Google Classroom, so you have access to that there. Oh, yeah. Yeah. All right, now, at the end of class today, like the last 20 minutes, I'm going to set you guys up with the rotational kinematic lab. So I'll talk about that when we get to it. But that might be a good time to, one of my top students, Cooper Basketball, some of you guys might know him, that he's an AP capstone, and he has a survey that he needs lots of people to take. So, yeah, if you can access that link at some point, that would help him out. We're going to do just one textbook question a day. So one textbook question, then I'll get you guys set up with this lab, and then you'll have the rest of the class to do that. Oh, also a side detail, there's something weird going on with my gradebook, so I can't actually access my gradebook right now. So sorry about that, but working on that behind the scenes. All right, so the one textbook problem we're going to do today is number 103 from your book. This one right here. We got a banner suspended from a horizontal pivoted pole, as shown in this figure. The pole is so many meters long and weighs so many newtons. The banner also has a weight and suspended near the end of the pole. There is a cable that's at the slanted angle. This didn't print out very well, but there's a cable at this angle right here. What is the tension in that cable? Okay, what's the tension? All right, so I'll draw you guys a better picture of that. I'm gonna, just like I normally do, pick up my own numbers. It's number 103, but otherwise it'll be a similar type of question. So we've got a wall. There's like a pivot point that a beam could pivot on, kind of like a door hinge. Oh, zoom out a little bit. Yeah. Okay. Let's get this beam going. And there's a, let's see what we got on this. There's the beam has a weight and a center mass, which is like right there. There's a banner that's some distance out here, and then there's a cable holding this all in check, okay, with some tension force. Okay, so draw this banner, something like that. Okay, so that's basically the setup right there. Okay. Now I need to give you guys some numbers. So how about some lengths? Let's have the length of this beam be, let me draw this. I'll make sure I don't get a bunch of vectors that are in the way of each other. Let's have the whole thing be 12 meters long. Okay, so 12 meters, because that's easy to divvy into these different fractions. Okay. So let's have the banner be at the 9 meter mark. So at 9 meters. Okay. And then the center of mass of the beam, let's put it at the geometric center, which would be 6 meters from the pivot point. Okay. So you guys see 6, 9, and 12 meters. Is that? Okay. I need to give you guys an angle for the tension. I'll call it 30 degrees. I think your book says 25, so it's pretty close, but 30-degree angles are usually a really nice number to work with. Right, let's draw some force vectors. Think of this like a free body diagram, like draw some force vectors on the beam, right? So from the perspective of the beam. Now there are a bunch of little forces. There's the weight of the beam. Now the weight, sure, it's distributed over the entire length, but you can treat the weight as acting right at its center of mass, and mathematically it works out perfectly fine. So I'm going to give the beam a weight of 200 newtons. 200 Newton beam. The banner also has a weight. I'm going to call it 100 newtons. So 100 Newton weight on that banner. You know what? I think that pen is seen better days. A different red pen. Okay, so those are two downward forces. Now there's a tension in this cable, but that tension is pulling at this weird angle. So I'll draw it kind of like that. And I'll label that T for tension. Okay? And that's the question is, what is that tension? But you know what? There's actually another couple of forces on the board. Well, actually, technically one more force on the beam. It's the force at the pivot point. Now, this beam, say you cut this tension, it would be free to rotate. Like, that's okay. But there's still some forces at this pivot point. The beam is being pushed into the wall by this tension because there's a leftward component on that tension. Right? And also, that pivot point is sort of holding it up. Now, I'll go ahead and label those two force. Well, it's actually two components, is what it is. But we're not going to solve for them. F sub x and F sub y. Okay. Now, those are not known. We could solve for them. Right? We could figure out what they are. Just not really curious to know. I'm really curious to know what is the tension in that cable. Maybe that could be like the possible breaking point. Maybe the tension could go up to like 1,000 newtons, and if it's more than 1,000 newtons, it's going to break. So is it going to break? Well, we're going to find out. Okay. Before I get break out equations and start plugging and checking with you guys see this 30-degree angle? What if this 30-degree angle was what if there was no angle? What if it was like 90 degrees? What if the cable was pulling straight up? Do you think the tension pulling straight up would be less than or more than what it is actually in the picture? Probably be a lot less, right? And then if you make it more and more, take this angle closer to 0 degrees, make this cable like really horizontal, it kind of makes sense that the tension would have to go up, 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 up. Like if it was oriented like the pin is right now, there'd be a huge tension. Okay? So think about like the geometry of like vector components. Maybe we'll go ahead and just draw these vector components. You guys did a lab way back in the day that involved spring scales and a bunch of different setups. Okay? But maybe it would help to actually draw these out here. You guys know that this angle is also 30 degrees. It's the same angle as have to be the same angle. Right? So this is like T sub x, and this is T sub y. Right? Those are the components. Right? Okay. Okay. And if this whole thing is just not moving, it's stationary, then it would be in equilibrium. And equilibrium is going to have, well, technically 3 conditions. I'm going to say the sum of the forces in the x direction is 0 newtons, the sum of the forces in the y direction is 0 newtons, and also the sum of the torque is 0 Newton meters. Okay? All the turning moment. I think I did a problem like this recently with you guys, maybe in the notes where I said the sum of the forces is 0. We were just looking in the y direction, but there's really x and y stuff going on. Right? Now this is really more details than we need to actually answer this question, but I mean that is a bigger, like broader picture of how it's going to work out. Okay? That's to say, here, if we go through each one of these conditions, here, this top one, the sum of the forces in the x equals 0. Well, there are 2. There's the x component of the tension, and there's this x component of the force from the pivot point. Those have to be the same magnitude. They have to be balancing each other out, so this thing isn't moving right and left. Okay? In the y direction, it has to be 0. Well, I see 2 forces in the y direction. Okay? There's a support force from the pivot point, and also a vertical component of the tension force. Okay? And then there's some weights, the weight of the beam and the weight of the banner. Okay? And these 2 up and these 2 down, have to balance out. Okay? But the way we're actually going to solve this is with this last condition. The torque has to go to 0. Now, I did tell you guys back in the day that technically you can pick any point and sum the torque about it, and it needs to 0 out for this equilibrium. But sometimes there's a point that's more opportune than other points. I like this pivot point, which is probably the most intuitive point anyway. We're going to treat this as the door hinge. I mean, it literally would be anyway, right? See this one select pivot about that point. Right? But the reason mathematically it's nice to pick this point is because some of the unknown values are at that point. So those unknown forces don't cause torque about that point itself from the reference, from the point of view at that point. It's kind of like if you go push on the door hinges of the door, it's never going to rotate the door. Okay. All right, so I'm going to pick this point right here as my pivot point. I mean, it literally is the pivot point. So the pivot point. Okay. And we're going to sum the torque about that pivot point. Take this last condition for equilibrium right here. The sum of the torque has to go to 0. Okay. You guys ready for that? And so that's the setup. And here we go. Okay. Relative to this pivot point, it looks like the weight of the beam itself is trying to cause a clockwise torque. See that torque? The banner is also trying to cause a clockwise torque. Right? Trying to make the whole thing rotate like this. Yeah. But the tension, well, that's holding it in check. Like something to do with counterclockwise. These torques are different, but just saying some kind of torque. Okay. Now those three torques should zero out. So I'll go ahead and set up an equation that says that. Well, you have to remember what the equation for torque is. Like the original way I told you guys is it's R cross F. R cross F. Okay, so there's a general formula. Okay. Set up an equation that balances out to 0 Newton meters of torque. Okay. So we got R cross F at the 6 meter mark. So 6 meters. I have 200 newtons of downforce. Maybe down is the positive direction, so the positive. So plus, at the 9 meter mark, I've got this banner that weighs 100 newtons. So at the 9 meter point from this pivot point, I've got 100 newtons of downforce. Okay. Plus, at the full 12 meter mark, 12 meters, I have, okay, now this is where the tension is acting, but this is also where the angle matters. Because, do you guys remember, go back to the definition of torque, R cross F. The fact that it's a cross product, what that means, the special kind of multiplication, that only the perpendicular values multiply together. Okay? So remember this tension at this weird angle, the x component is not actually causing any rotation. Right? I mean, part of the tension is actually pushing this beam into the wall, but that's not causing it to rotate. Only the y component is. Only this component right here. Isn't that true? Only the y component's actually doing anything. Right? So it's really tension in the y direction that acting at the 12 meter mark that's causing the counterclockwise rotation that's bringing this all to 0 Newton meters. Okay? So take this last condition, sum of the torque is equal to 0. Okay? You've got 3 torque values, and they have to zero out. Okay? Now, if you can get that far, then we're actually most of the way through the problem at this point. So just do a little bit algebra cleanup and solve for ty. So I got 6 times 200 plus 9 times 100. This all comes out to 2100. I'm going to subtract that over. So 12 meters times ty, t sub y, right, is equal to negative 2100 Newton meters. Divide both sides by 12 meters. And I'm getting tension in the y direction is 175 newtons. Okay? And it's negative, and the negative just means it's acting upward, which is the negative direction. Okay? And now that's not what your book asked you for, but that is a really critically important middle step. Okay, guys got that? Okay. Right, so just to recap what we got so far, on this beam, some relative to this pivot point, the weight of the beam itself and the banner trying to have it go clockwise. Yeah, clockwise. The vertical component of the tension is holding it back counterclockwise, and we just figured out the magnitude of that vertical component of the tension. Now, that's not the full tension, though. That's just the vertical component. Okay? So let's go back and look at the geometry to figure out the full tension. Do you guys see like a triangle shape right here? See that right triangle? Here's a right angle. I mean, did it by figuring out the components. Okay? Hey, what is the relationship between this number, which we now know to be 175 newtons magnitude, okay, and this hypotenuse of the right triangle, and this angle? Right, so bouncing off this 30-degree angle, do these two sides of the triangle have a sine, cosine, or tangent relationship with each other? Which one is it? Sine, cosine, or tangent? See, got the hypotenuse, so it's not tangent, it's either sine or cosine. And this leg of the triangle is opposite of the reference angle. That means it's got to be which one? Cosine. It's got to be sine. Yeah, it's got to be sine. Right? So I know that sine of that 30-degree angle, right, sine of 30 degrees, is opposite over hypotenuse. That's t in the y direction. Well, I'll just list the magnitude as 175 newtons divided by the full tension. And the full tension, that's what we want to know. Okay, that's what we're curious to know. I read this like the definition of the sine of this angle. Okay, you guys get that? All right. Okay. All right. So do a little bit of algebra switcheroo. The tension is going to be cross multiply that up, divide the sine of 30 degrees down. 175 newtons divided by sine of 30 degrees. Oh, by the way, sine of 30 degrees that might be something you could possibly memorize, or maybe some of you guys have. Does anybody remember what sine of 30 degrees is? It is a half. Yeah, it is a half. Okay. Now, if you divide by a half, isn't that like multiplying by 2? Here, I'll show you guys. 175 divided by sine of 30 degrees. Yep, 350. So the tension in that cable is 350 newtons. Yeah. Okay. Now that you know the answer, let's go back and just cement the bigger context. Okay. Notice there's only 300 newtons acting down. Right? The weight of the beam and the banner together is 300 down. Okay? And what there's more than that in the tension? Yeah, because remember the tension isn't just acting vertically; it's really acting at this angle. Okay? And then this could answer a question like the question I asked near the start: if this tension can go up to say 1,000 newtons, for example, is it going to break? Well, in this case, no, it's safe. Right? It's got plenty of tension that it can hold. Okay, so good. Guys, good. All right. All right. So let's put all the torque stuff to the side, and I've got for you guys a short lab, mostly just to get your hands on these turntables, and this is going to be a rotational kinematic lab. So back on the lab tables are a bunch of turntables, and I'm going to put some of these lab pages out, and but let me take you guys through this lab page to show you exactly what I'm looking for. Okay. So this is not really supposed to be that complicated. So first, you guys see this diagram? Got a turntable, got some object near the edge, measures the radial value. Let me turn this upside down. Got some points marked out. Okay. So from the center point, let's say I want this as my reference point out here, or you can pick a point on the edge. That's okay, somewhere out there. Let me see what's the distance. I'm looking at 12 centimeters. You guys see 12 centimeters? Okay. So if I had this lab page, and I've only got enough prints for one per team, so you guys can put several names on paper. I'd write 12 right there for 12 centimeters for the radius. Okay. Okay, so first number, check. All right, then I want you guys to do sort of like a two-part story. Okay? And it says exactly what to do. It says 3 revolutions at constant angular velocity. So that'd be like this. 1, 2, 3. Okay, you guys can do that, right? Hey, theta is 6 pi radians. Do you guys remember that 1 revolution is 2 pi radians? So 3 revolutions would be 6 pi radians. Yeah, and I gave that to you guys already. Okay. Somebody time that. You guys see time in seconds? Could you guys time that? How many seconds it takes? Could you guys figure out the angular velocity by taking how far it turns in radians divided by how much time? Right? You guys do that? Right. What you guys might do is, you guys see these posters hanging up here on the wall? Right? You might take advantage of those kinematic equations that are listed right there, or maybe in your notes. Okay? Right. Then, also attached to that story says, how far did it go in centimeters, that point near the edge? And how fast was it going in centimeters per second, say if you pointed a radar gun at it? Now, these are linear values, but, well, you guys can see on those printed posters up there, too, that all you have, wait, did I print these out? I think I... Yes, I did. All right, this will be great for the camera, too. Okay, so to answer some of these questions might help to take advantage of these kinematic equations. And to answer what's the linear equivalence, like how far did it go in centimeters, how fast is it going in centimeters per second? Okay. Do you guys remember to translate from rotational information to linear information, you just multiply by r? You guys remember that? Okay, so you guys got all this. Okay. All right, so that's part 1, just rotate it 3 times at a constant rate. Part 2 says release it and allow it to slow to a stop. So let me do the full story right here. So you're going to pick up the point, go 1, 2, 3, and then just let it go, and just let it go to a stop. Okay. Now that time that it comes to a stop, somebody timed that, and also count how far it turns in radians. Now this box right here is probably the trickiest number to figure out on the whole page, because you have to figure out how far did it turn in radians. What might be helpful is to count revolutions or degrees and just convert radians. You guys remember 1 revolution is how many radians? 2 pi. And that's also equal to 360 degrees if you count that way. Okay? So figure out how many radians it turns. Okay? Time, how long it takes to come to a stop. Okay? Your final angular velocity, of course, is going to be 0 radians per second because that's what coming to a stop is. So just printed that number. Figure out what is the average angular velocity. Now, this is something that we don't talk about very often in this class, but isn't that just how far it turns divided by how much time, right? How far did it turn in radians divided by how much time should give you the average angular velocity, right? Don't see that very often in this class. And then can you figure out the angular acceleration? What rate was it slowing down? Now, to do that, you want to play off these formulas. So, for example, if you know final omega is 0 because it comes to a stop, if you know initial omega, which just comes from say this part here, wherever you released it, and you know how much time it took to come to a stop, that would be this number here. Then, could you guys go back and calculate what this angular acceleration is? Okay, good. It's plug in my new voice here. So fast. Okay, and then can you figure out the linear equivalence of all those rotational values? So spinning to a stop, how far did the stop on the edge travel in centimeters? That's just theta times r again. That's just going back to this. Okay. Can you figure out let's say like average speed? Now obviously it's slowing down the whole time, it's slowing down. So but the average speed, that would just be omega average times r. And then can you figure out tangential acceleration? So that'd be like the rate you're hitting the brakes in a car, like the rate you're slowing down, sort of in a linear sense at any instantaneous moment, in centimeters per second squared. Is that okay so far? Okay. And then one last thing with SLAB are the graphs on the back. Okay, so this is our classic x versus t, v versus t, a versus t, which we've done a ton in this class, and also the rotational values, theta versus t, omega versus t, alpha versus t. I'm going to do one of these graphs with you, and then you should be able to figure out the rest of them from there. Let's look at the omega versus t. That's what this title says. It's print small, but camera can see it. So omega in radians per second as a function of time and seconds. Okay, so let's do this graph. Okay. Now I listed one time value. This is it says t naught. That's the time that you release the disk after you spin it 3 times. Just let it spin to a stop. Okay, that's exactly right there. So for the first 3 revolutions, you're just going to spin at a constant rate. So wouldn't that be a constant angular velocity, just like that, for the first 3 revolutions? Okay. And then right at t naught, whatever time that is, take your finger off, just let it spin to a stop. And okay, well, if it's spin to a stop, isn't it just going to go down like that? Right? So that's one of those graphs. I bet you guys could figure out the other 5 based on that. Okay. All right, I will leave that to you guys there. So everything you need back in the lab stations, walk around, help you guys out. At the end of class, just pop that in the grade tray.